Imagine you're floating in deep space. No stars nearby, no planets, just darkness stretching in every direction. You can't tell which way is up or down. There's no sound, no wind, no sense of distance, just you and the universe. Now imagine someone hands you a telescope. But this isn't a normal telescope. Instead of zooming in, it zooms out. Farther out than any camera ever built, farther than any spacecraft has traveled. You raise it to your eye, and slowly, you begin pulling back. Past Earth, past the solar system, past our galaxy, past everything we've ever observed. And the question guiding this journey is simple. What is the biggest thing in the universe? Is it a galaxy, a cluster of galaxies, or something even larger, something we rarely think about? To answer that, we start small, right here, close to home. Right now, you're looking at Earth. From the ground, Earth feels enormous. Oceans span thousands of kilometers. Mountains rise kilometers into the sky. But from space, Earth becomes something else entirely. A small blue sphere orbiting a star. That star, the Sun, is vastly larger than Earth. Its diameter is about 109 times wider. In fact, you could fit more than 1 million Earths inside the Sun, and yet astronomers don't consider the Sun especially large, not even close. There are stars like Betelgeuse or UY Scuti that are hundreds or even thousands of times larger. If one replaced the Sun, its surface could stretch past the orbit of Mars, maybe even Jupiter. So stars can be enormous, but stars still aren't the biggest structures in the universe, because stars rarely exist alone, they live in families. Zoom out a little further. Now you see an entire solar system, 8 planets, more than 200 moons, millions of asteroids, and distant icy objects drifting in the outer darkness, bound by gravity, all orbiting the Sun. But here's something strange. Most diagrams of the solar system are wildly misleading. In textbooks and posters, planets appear close together. In reality, space is mostly empty. Imagine shrinking the Sun to the size of a basketball. Earth would become a tiny grain of sand orbiting 26 meters away. Mars would be about 40 meters away, and Neptune nearly a kilometer away. Between them is almost nothing. The solar system still isn't very big compared to what comes next, because our star is just one of billions. Zoom out again. Now something spectacular appears. Our home, the Milky Way. The Milky Way is an enormous rotating disk of stars, gas, and dark matter. It contains somewhere between 100 and 400 billion stars. That's hundreds of billions of solar systems. If the solar system were a coin, the galaxy would be North America. Across the universe, there are hundreds of billions of galaxies, elegant spirals, smooth ellipses, chaotic shapes formed through collisions. One of the closest is the Andromeda Galaxy. It's 2.5 million light-years away. In about 4 or 5 billion years, the Milky Way and Andromeda will collide and merge into a single giant galaxy. But even galaxies, vast islands of stars, are not the biggest structures, because galaxies gather, zoom out. Gravity pulls them together into galaxy clusters, enormous collections containing hundreds or thousands of galaxies. Each can span millions of light years. Our Milky Way belongs to the local group, a small neighborhood. Yet clusters themselves organize into superclusters. These are among the largest known gravitational structures. Our galaxy sits in the Laniakea Supercluster. Its name means immense heaven, 500 million light-years across. For a long time, we thought superclusters were the limit, until we mapped the universe in detail. Galaxies are not randomly scattered. Instead, they form enormous filaments, long strands connecting everything, like highways. Between them lie enormous empty regions called cosmic voids, some hundreds of millions of light-years wide. This structure is known as the cosmic web, the largest known pattern of matter in the universe. It looks like foam or a sponge. Or the branching pattern of neurons in a brain, representing the ultimate scale of matter. But eventually, we run into a limit, keep zooming out, past the filaments, past the entire cosmic web, to a strange boundary. Not a wall, but a limit of visibility. Beyond this distance, we simply cannot see, because light hasn't had enough time to reach us. This boundary defines the observable universe, 93 billion light-years across. Inside is everything. Every galaxy, every cluster, every filament, every star we have ever detected. From our perspective, this is the largest region that exists. But there's an important twist. The observable universe is not the entire universe. It's just the part we can see. Think of it like standing in the middle of a foggy field. You can only see a certain distance before the fog hides everything, but the field likely continues far beyond. The true universe may extend far beyond the boundary. It might even be infinite. The biggest thing in existence might simply be the universe itself. So why this structure? The answer starts shortly after the Big Bang. In the first moments of history, the universe wasn't perfectly smooth. Tiny quantum fluctuations appeared, ripples in density. Over billions of years, gravity amplified those tiny differences. Slightly denser regions attracted more matter, which made them even denser, eventually forming stars, galaxies, clusters, giant cosmic filaments. Smaller regions became voids. Everything grew from ripples smaller than an atom. So what's the biggest thing in the universe? It depends on what you mean by thing. If you mean a single connected structure, it's the cosmic web. If you mean the largest region we can observe, that's the observable universe. But truly, it is the universe itself. Everything we've ever known, every star, planet, and atom in your body, exists inside a tiny fraction of it. When you zoom out far enough, the most surprising discovery isn't how big the universe is, it's how small our corner of it really is, and how much more might still be out there.